Okay, without any further interruptions, I'm going to get into the content. Sorry about that. Okay, so the basic units. The basic unit of all electrostatics is charge, which is written as Q, has the unit of coulombs. Electrons have an elementary charge of -1, as you might know from your general chemistry class, and protons have an elementary charge of +1. But in terms of physics, that's not actually how we consider charge, right? In physics, we consider charge in terms of coulombs. And in physics, an electron has a charge of -1.6 times 10 to the -19th coulombs, right? It's not necessary to memorize this. I doubt they'll be asking you about it, like what the charge of an electron is. They'll usually give it to you. And if you want to know the charge of a proton, it's exactly the same as this, except it's positive 1.6 times 10 to the -19th, right? And most of the time, they won't just be asking about maybe an electron. They'll be asking about some kind of atom, which has multiple electrons and a different charge. But this is just something I wanted you guys to know, that the chemistry definition of charge and the physics definition of charge are very different. They use different units. In chemistry, we use elementary charge, which is -1, -2, -3, +1, +2, +3. In physics, we use coulombs, which is a concrete number instead. Okay. Next, I want to talk about what the electrostatic force is. So if you remember from our force lecture, we talked about mechanical forces. So we talked about tension, normal force, gravity, friction, all of those. So in addition to the mechanical forces, we also have an electrostatic force. And the electrostatic force applies to anything that's electrically charged, any particle that's electrically charged, like say protons, electrons. When we actually consider real physical things like say me or this pen or a water bottle or whatever, they technically do have electrostatic forces with each other, but most of the time, or most time they do have electrostatic forces, but electrostatic force is so small that it doesn't play a role when you're talking about big things. But when you're talking about small particles like protons, electrons, atoms, and anything like that, then electrostatic force is a big factor, more so than even gravity, right? As I mentioned, everything experiences gravity, right? Even the small particles like electrons, they have some kind of mass and they experience a gravitational force, but because they have such small mass, it's relatively small compared to the electrostatic force, okay? Just like all forces, it's a vector. Electrostatic force is a vector, has a magnitude and a direction. The magnitude of this force is equal to this formula, Fe, which is the electrostatic force, is equal to K, which is Coulomb's constant. And it's a constant, I didn't even put it here because I don't think you should memorize it. They'll always give it to you along with its units, right? Q1, Q2, which are the charges of the two particles that we're looking at. So if we're looking at a proton and an electron, Q1 would be the charge of the proton, Q2 would be the charge of the electron. And all of this over d squared. D is the distance between them. So again, if we're looking at a proton and electron, d would be the distance between the proton and electron in that specific case, okay? If you notice, actually, if you were here for the mechanical force lecture, or if you just remember from your physics class, this is almost exactly the same as the formula for force of gravity. If you remember, force of gravity is Fg equals big G, which was a constant, M1, M2 over R2, right? Where M1 and M2 are masses, and R2 is the distance between the two objects. This time for the electrostatic force instead of the gravity force, we use charge. Q1 and Q2 are charges instead of mass. So Q1 would be the charge of the first atom. Q2 would be the charge of the second atom. Like I said, if we're looking at one proton and one electron, Q1 would be the charge of the proton, Q2 would be the charge of the electron. If we're looking at two electrons, Q1 and Q2 would both be the charge of the electrons. And instead of G, which is the constant for gravity, you use K. K is the is Coulomb's constant, right? Because Coulomb was the one who kind of found this out. And like I mentioned, I'm not including it here, but they'll always give you Coulomb's constant in a question or in a passage or anywhere, along with the units. They'll give you the value and the units, right? And they'll always tell you that it's Coulomb's constant. So you don't have to memorize it, okay? And this is the equation to find the magnitude of the electrostatic force between any two charged particles, right? Protons, electrons, atoms, anything that has a charge. The direction of this force is different from what it is for gravity. If you remember, any two objects, no matter what objects or their masses or their sizes or the distance or anything like that, the gravitational force between two objects is always towards each other. So for example, I have this pen and I have myself or my hand right here. My hand and this pen have a gravitational force between them, right? It's very small because very small objects, but there is a gravitational force. The direction of the gravitational force is always towards each other. So from the force of, the force of my hand onto the pen is towards my hand. So it's going this way where my finger's pointing. From the pen onto my hand is in the opposite way. It's towards the pen. So it's this way, right? It's always towards the other object. However, in electrostatic force, this is not always the case. In electrostatic force, it depends on the charge. If the charges are like or they match, so for example, if both particles have positive forces of positive charges, or if both particles have negative charges, if they're the same charge, the force is actually away from each other, which is not like gravity. So if the pen and my hand were both protons, the force would actually be these ways, right? It would be away from each other, right? It would be a repellent force. However, if they were opposite charges, say a proton and electron, as you may remember, it's towards each other. Okay. All right. I actually want to give you guys the first poll question. It's a little bit early, but just based on what we've been covering so far, with direction and magnitude of electrostatic force. So this uses very simple numbers. Usually you won't see numbers this simple for charges, at least for coulombs, like +2, -5, -1. But this is just so you learn the idea, right? Now I'm going to start a poll, right? There's 4 answer choices, A, B, C, and D. And there's also another option where you really don't know. And what the question is which, sorry, did you mute whoever that was? I was echoing off of, okay. And the question is, which way will this particle move as a result of these two particles? Will it go this way, where A is pointing? Will it go where B is pointing? Will it go where C is pointing? Will it go where D is pointing? Okay. Okay, please take about another minute or so. And as a hint, remember to take into account both direction of the two forces and also the magnitude of the forces and how that would affect the vectors. Okay, that makes sense. But I'll go over it in about 10-15 seconds. So please get your answers in. I'm going to close the poll. So the most popular answer was A, with B being a close second. C and D were not very popular. However, the correct answer actually is C, right? So let's go over this. So first thing I want you guys to remember is direction, right? And when you see something like this, you would always, first thing you would look at is direction. So the forces being applied onto this middle particle are from these, both of these, right? Because I said anything that's charged is an electrostatic force. So what would happen is this is a positively charged and this is a negatively charged, right? So that means the direction of the force would be towards, right? Because they're opposite charges, they attract. So it would be towards. So this one moves towards this +2. So it would be going this way. This one, but it also has an interaction with this one, right? Because they're both negative, -1, and -5, the direction is away because like charges repel, right? What is directly away from this? It would be this way, right? So if I would draw it again, this is the -1 coulomb particle. It has a force going this way and a force going this way. Now we have to add up these forces because forces are vectors and we have to add them together to get a net force or a total. Again, we break them into components to do this. So you would have an upward component for this one, a leftward component for this one, a downward component for this one, and a leftward component for this one. Now we want to just add together all the components in the same direction. So for example, in the x plane, we see there's a leftward component and a leftward component. So the net force in the x plane is leftward. And then we have an upward component and a downward component in the y plane. So normally this might cancel out. And if it cancels out, you would get something like B. But the y component in the up direction and the y component in the down direction are not equal in magnitude, right? One of them is bigger than the other. What is the magnitude of an electrostatic force determined by? It's determined by Coulomb's constant, which is the same no matter which two particles you look at. So that's not the case. It's determined by distance. They should have, the question actually should have specified that they were equidistant from each other. So 1, -1, it's like all three of these are equidistant from each other. So this distance, and this distance are equidistant, meaning that distance wouldn't have been a factor. And lastly, it's the charges themselves, right? Now, if we look at the charges themselves, between these two, it's -1 and +2. When you multiply that together, you get a charge. When you multiply the charges together, you get +2. However, when you multiply this one with this one, you get a charge of -5. Therefore, the one that's -5, or where the charge multiplies make 5, is actually much greater, right, in terms of magnitude than the force between these two. Because of that, the downward component due to this one is actually slightly greater than the upward component due to this one. So this gets completely canceled out, but this only gets mostly canceled out. There's still a slight downward component. So that means there's still a slight downward component. When you add these two net components together, you get a down left component, which is this way. And that corresponds to answer C. I know that was a little bit confusing. It was a bit long. Does anybody have any questions or anything you want me to go over again? Anything you want to ask? Before I move on. Okay, so someone asked, why is the upward one canceled? Okay, so you see how this charge has an upward component and a downward component? Normally, up and down cancel because up and down are opposite directions, right? If you go a little bit up and then you go the same amount down, well, you just ended up exactly where you started, right? However, in this case, the upward component was larger than the downward component. So for example, say you moved 10 feet forward and then 8 feet backwards. So ultimately, in the end, you still moved a little bit forward. You moved about 2 feet forward, right? That's because the amount you moved forward is more so than the amount you moved backwards. If the upward component and downward component were exactly equal, say 10 feet forward, 10 feet backwards, you ended up not moving. And the leftward force wasn't canceled out because in order to cancel out a leftward force, you need a rightward force, right? To cancel out. In this case, what had happened was you moved 5 feet left and then you moved another 7 feet left, right? When they're in the same direction, you actually add them on top of each other, right? So if you want to think about forces in any way, think of it as you're actually physically moving, right, in the direction of the arrows. If you had a force that was going up left and then a force that was going bottom left like this, well, what would happen in real life if you moved forward and left, and then from there you moved backwards and left, right? From where you initially started, if the forward and backwards were exactly equal, you would have only just moved left. If the forward was slightly more than the backwards, you would have moved a little bit forward, but a lot to the left, right? Does that answer any questions? Forces, because I'm not coming back to forces for pretty much the rest of the lecture. This is all we're going to talk about, electrostatic forces. So if you have any questions, now's the time. Yes, the upward force is more because of -5, right? This one is you're using charges. So if you remember, I'm actually going to clear everything. If you remember, the formula was Fe equals K Q1 Q2 over D squared for each of these, right? K is the same for all, no matter what, K is always the same, right? D squared, I said these were equidistant from each other, so the distance is exactly the same for both situations. The only difference is the magnitude of the charges. If you multiply -1 by -5, you get 5, and that means the Fe would be 5 times all of these other variables, whereas in here you would multiply -2 or +2 by -1, and then you take the absolute value of it, you get 2 times K over D squared, right? 5 obviously bigger than 2, so this one has a stronger force, right? And because this one was pushing it away in this direction, right? The downward from this cancels from over. It's more downwards than it is upwards. If that makes sense. So that's why the total is downwards. I'm sorry, whoever that was, can you please mute? Yeah. Do you have a question? Okay. Any last questions before I move on? Okay. -6 instead of -1. If it was -6 here, if it was -6 here, the result will be exactly the same, right? Because it would be -6 times 2, which is 12, or -6 times -5, which is 30. This one's still bigger. 30 is still bigger than 12. If this one was -6 and if instead this was if this was +6, then that would be different, and then the answer would be A. If this was +6, then this force would actually be more so than this force. So it would be A would be the answer, because it'd be the upward would be stronger than the downward, so it'd be going a little up, but it'd still be going mostly to the left, so it'd be A. Does that make sense? Okay. Yeah, like charges repel, opposite charges attract. So negative and positive go towards each other, negative and negative go away from each other. Okay, moving on. If you guys have any questions, please stick around to the end and ask me then, but I want to move on with the lecture. So I want to talk about current now. So current is a measurement which tells us the amount of charge running through a certain point over time, right? It has units of amperes, or A is the symbol, right? And the symbol for current is I. And the other units for amperes is coulombs per second. Because the units are coulombs per second, one equation that we can use to find current is actually I equals Q over T.
All right, later on.
Where Q is charge and T is time, right? If you look at the units for Q is coulombs, unit for T is seconds. So coulombs per second is Q over T, right? This is an important equation that you probably should know. Okay. For current, okay, and just remember amperes are equal to coulombs per second. Remember the units. I can't stress that enough, especially for electrostatics, circuits, and anything like that in physics. Remember the units, right? Units are very important because they'll help you solve problems that you may have forgotten a formula for or something like that. Next is voltage. Voltage can also be defined based on charge. It, however, also uses work or energy. So the units for voltage are volts. Voltage is written as capital V, and volts, the unit, is written as lowercase v. The units for volts are also can be joules per coulomb. Okay. Because of that, we have the equation voltage equals work over charge, or voltage equals energy over charge, right? Again, looking at the units, what joule per coulomb means joules on the top, coulomb on the bottom. Coulomb is equal to charge. Joule is equal to either work has units of joules, or some kind of energy, right? Okay, that's for voltage. Now, and this is why I said units were important. If you just followed where I was going with units for voltage and for current. So remember from one of our previous lectures, we had power. Power had units of watts, and the equation for power was work over time. We can also remember that current equals charge over time, right? Notice how if we do power over current, we can get time in the numerator and time in the denominator. So they cancel out, leaving us with only work over charge, which is equal to V. Let me write that out for you guys, okay? So we know that power is equal to work over time, right? So if we had work over time, okay, and then we multiply, and then we actually, if we divided that by current, right? And you remember that when you divide something, when you divide a fraction, you just multiply and flip it. So it's now time over charge. Right. Now look, time and time cancel out when you multiply these, and you're just left with work over charge, which is W over Q. And now look, when you did power divided by current, you were left with work over charge, which is equal to voltage, right? So this is another important formula to finding voltage is doing power over current. So if you know how many watts some electrical device has, how many watts are running through it, and you also know that the current, the amount of amps running through it, you could find the voltage, right? However, you might not have remembered this on the MCAT. You might not remember this formula, you might not have seen it or something like that. However, if you are given the power, right? If you're given how many watts something is, you'd be able to think, well, what is watts equal to? And you should be able to think on the MCAT, what is watts equal to? Watts is power. Power is work over time. Work over time is joules per second, right? J per second. And then you're also given a current. You know, current is equal to Q over S, right? And then from here, you would actually be able to, like I just showed you right now, you actually are able to derive this formula just knowing the units, right? If you know what voltage is equal to, or what a volt is, and a volt is a joule per coulomb, then just having these two units, you'd be able to figure out how to find voltage just using these two if you didn't remember this formula, right? And that's what I wrote here in the bottom, especially for electrostatics, which has a lot of related equations in units. Try and remember what each unit means. Like for example, an ampere is a coulomb per second. Doing this will make it easy for you to derive a formula like V equals PI on the spot if needed. Right. That's just a helpful hint that you might need on the MCAT. All right. Any questions before we move on to circuits on anything involving power, current, charge, voltage, anything so far? If not, I move on. Okay. Now we want to talk about circuits. So the first thing you should be able to do is read a circuit diagram, right? The main components, and circuit diagrams can get very, very complicated, especially if you go into some kind of engineering field like electrical engineering, computer engineering, or something like that. For our purposes and for the MCAT's purposes, we're going to keep it very, very simple with the circuits. The only components a circuit will have would be some kind of battery or voltage source, a resistor, and a capacitor, and possibly some kind of voltmeter, right, just to measure the voltage. Okay. And here I've drawn, or I've included a picture where this is a resistor. This is what it looks like. It's a squiggly line like this. Then this is what a capacitor looks like. It looks like a plate, right? Looks like that. That's how you know it's a capacitor. And then you also have a battery, which can look like this here. This is a battery. This is a specific type of battery. I believe this is a AC/DC battery, but most batteries or voltage sources that you'll see will actually look like this, right? And I've drawn and I've included it here, right? This is what a battery will look like, but all batteries will have a voltage next to them like this. So for example, 10 volts, 20 volts, 30 volts, whatever. It's important to know what each component of a circuit looks like, right? And like I mentioned, these are the only components we'll be looking at here. And a voltmeter, actually, I'll show you, looks like this. So if we had this circuit, and then it would look like this, then it should have a circle here and it should say like a V here. Right, and that's what the voltmeter would look like, and it would check the voltage in between this area. Or the voltage drop, I should say, between that area, the difference in the voltage between these 2 points, right? But other than that, there shouldn't really be any other any components you should have. They may have frequency. That's more related to like I mentioned, AC/DC batteries. That's, you don't really have to worry too much about that. Frequency in terms of circuits, right? That's just something with this picture included as well, right? Because of this specific type of battery, I think. Okay, for our purposes, we're not really going to be focusing on that. For our purposes, next we'll be looking at Ohm's Law, right? And this is a classic formula that I'm sure you've seen many times in your undergraduate physics courses. It's basically the fundamental equation you'll use for almost any circuit problems. Almost any circuit problem will require you to use this in some form. And it's V equals IR, voltage equals current over resistance. And you can also easily rearrange this depending on what exact component you're looking for. If you're looking for the voltage, the current, or the resistor, for the resistance, you can make it I equals VR, R equals IV, and just rearrange this equation. But the basics is this one, V equals IR. Okay. Next, I want to talk about Kirakas Law. This is also a relatively simple one, and one we're not going to cover too in depth. But I just want to talk about. it. Kirakas Law is the current in and out of any node is always equal. So, for example, here I've drawn this circuit diagram right here, and if you imagine this is like a wire, like a circuit, this is a node where something splits, and it started off here. This is I1 is the current running through this one line, I2 is the current running through here, and I3 is the current running through here, right? And then you can do this, I1 equals I2 plus I3, right? Because going into this one point, this one node, all of the current going in must equal the current coming out, right? You can't like just get rid of current, or you can't just make current out of nothing. Similar, I guess, if you want to think of it, it's not exactly, but if you want to think of it similar to mass or energy, you can't make it or you can't get rid of it. In a reaction, this is kind of similar. If you have any node, any current that goes in must come out, right? And assuming these two are equal, I2 plus I3 equal I1, however they may be split up, right? So for example, the current in I2 could be greater than the current I3. They don't necessarily have to be equal to each other, but when you add them together, they're equal to I1. Somebody raise their hand. Opal, if you want to ask a question.
Yeah. It had to do with the circuit diagram really quickly. I just wanted to look at that unit again for mu. Is that the mu microfarad? And is that units? What's the microfarad?
We're gonna come back to units in a bit. I just want to show you what they look like. I want to show you what the actual components look like.
We can come back.
But it is microfarad and microfarads. It's the units for capacitors, but I'll get to that later. I don't want to confuse people.
Okay.
Right. Next, I want to talk about, and this, like, I would honestly recommend just taking a picture of this whole screen and then just memorizing everything here, except for maybe this. This you don't really have to know. This is more for electrical engineers, but this is not for us. But all of this is extremely important. So there's two types of circuits, right? There's series circuits and there's parallel circuits. Series circuits are anything where things are wired in series. And the way you know how, if something's wired in series, if it's continuous, right? In one line. So for example, this is a circuit, this square box, this is the battery, right? The current goes like this, travels here through one resistor, then immediately through a second resistor, and then immediately through a third resistor. These three resistors are wired in series because they come one after the other on the same, if you want to think about a line, or on the same wire, right, on the same path. That's what you call being wired in series. Something like this is wired in parallel. And look, if you follow this line, it actually splits here and here, and then again here and here. These three resistors are wired in parallel. They come from one wire that's been split three ways, right? And then they reconverge here, and they go here, and they reconverge at this node. They split at this node, and then they reconverge at this node over here on the bottom, right? This is the difference between being wired in series and parallel. And if they're wired in series and parallel, there's different rules. So for example, the voltage in a series circuit, the voltage at 0.1, 0.2, and 0.3, they're not equal to each other, but rather they add up to make the total voltage that was put in. So for example, if you had a 60-volt battery, voltage at resistor 1, voltage at resistor 2, and voltage at resistor 3 would all add up to be 60 volts, right? The current, however, is equal at points 1, 2, and 3. And this is, again, if you want to think of it like in Kirakas Law sense, if this is a node, this is node 1, there's one line going in and there's one line going out. If there's one line going in and one line going out, that means both the line going in and the line going out must have the same current, right? The current hasn't changed because there's only one going in and one going out. Okay. And the resistances are very simple. You just add them together. So to find the total resistance of the circuit, right? Each of these resistors has their own resistance. So for example, this one might be 2 ohms, and we'll cover the units a bit, 3 ohms and 5 ohms, right? But the total resistance of the circuit is the addition of all of them, the sum of all of them, which in this case is 10. For parallel circuits, it's different. The voltage at each point is the same. So here, here, and here, the voltage is the same. The current, however, is different because, again, if you remember Kirakas, you had some current going in, but then it was split into three ways, right? split into this path, and this path, the current, right? So the current at these points sums up to be the current in this one line, but because it was split up, it's not equal. And the resistance is found this way. It's 1 over R1 plus 1 over R2 plus 1 over R3 equals 1 over R total. So for example, if you had something like, if the resistance for all three of them was 2, so it'd be 1/2 plus 1/2 plus 1/2, which is equal to 3/2. But then because it's 1 over R total, you actually flip what you get. So it's actually 2 over 3. And the total resistance of the circuit is 2/3 ohm. Right. Any questions about this before I move on? Okay. So I wanted to actually, based on the definition I gave, I wanted to ask this question about, is this circuit in series, parallel to both? Is it neither? So please answer this. I'll start a poll in a second. Okay. And this is not necessarily a question you might see on the MCAT. This is a question that I've included because I wanted to kind of gauge your understanding so far. Okay, so please give this a try. Okay, take another 10-15 seconds to get your answers in. Okay. So 78% of people picked answer C, both, which I'm very happy about. So it actually is both. It's a compound circuit, right? It's a combination of a series circuit and a parallel circuit. If you notice, these two resistors are in parallel because you have this one branching node that splits into two nodes, right? So this is in parallel. But if you look at both of these combined as one resistor, right, they're actually together in series with this resistor because they're on one line, right? So if you want to do this, and then it gets to this point where you have this whole compound, and then you go back to this, right? So it's actually both. How would we work with this, right? Well, we use the same exact rules that we use for anything else, right? First, you would just find the total resistance of these two together, as if they were just two resistors in parallel, and then you would just combine that to get a total resistance of this combination, and then you would just do you'd add that to this in series. Let's give an example. For example, 1 over 18 plus 1 over 9, or 1 over 9 can be rewritten as 2 over 18, which is equal to 3 over 18. And this I'm using the formula for finding total resistance of a parallel circuit, which is 1 over R1 plus 1 over R2 equals 1 over R total, right? So you get 3 over 18, and then you, again, You just flip it. Whatever you do when you add these up, you flip it. So it's 18 over 3, or which equals to 6 ohms. So the total resistance of this whole circled area is 6 ohms. Right? This whole thing together is 6 ohms. Each one, this one is 18, this one is 9, but together there's 6. Now this whole thing together is in series with this one. So what you would do is to find the total resistance of everything, of this everything, you would now do 4 ohms plus 6 ohms equals 10 ohms. Right? And that's because we're using the series resistor rule, which is R1 plus R2 equals R total. R1 is 4, R2 is 6, R total is 10. Very easy, very simple. Okay, any questions before I move on to another poll question? Somebody asked if you could have done, so no, because I'm pretty sure it doesn't work, but the reasoning behind it is these two together aren't parallel. So in order to consider this in series to something, it has to be into this whole circle. So like this circle and this circle have to be added together, right? You can't add this circle to a part of this circle and then do it that way, right? You have to add the two circles together, right? There's two circled areas. So you have to do this 4 plus this whole thing. The value of this whole thing is actually just 6, right? And the way we found that is by considering these two in parallel. Right? Does that make sense? Okay. All right. I'm gonna start the poll question. Take the time, and you are gonna have to like I mentioned, use like the rules that I gave before, not just for resistance, but for voltage and current as well. Okay, guys, please take another 30 seconds to a minute to answer this. And like I said, I'll go over it at the end. Okay. In the polling. So the answers are fairly mixed. C had a slight lead, and correct answer actually is B. But it was very mixed, right? It was about 25% B, C, D, and not sure. Okay, so let's go over it. Right, we know that each resistor is 2 ohms, right? So A, B, and C are all 2 ohms. Doing this, and we also know that the voltage, so VT, V total, is equal to 12 volts, right? First thing I would suggest doing always is finding R total. So R total, right? Because once you find the R total, you already have V total, you'd be able to find the I total, right? Because I total is just V equals IR, right? So V equals IR, right? You'll be able to do this to find the I total, and then you can work from there. R total is equal to, first, again, these two in parallel, right, to each other, A and B. So RA, 1 over RA plus 1 over RB is equal to 1 over RAB, right? 1/2 plus 1/2, because each one is 2. 1/2 plus 1/2 is equal to 1, right? So 1 ohm. It's equal to 1 over 1. When you flip 1 over 1, it's still 1 over 1. So it's RAB is equal to 1 ohm. And then RAB and RC are in series, right? This whole thing and this little thing are in series. And so you do RC plus RAB. And RAB is the parallel, is the combination of these two in parallel, right? We said this was 1. This we know is 2. So RT is equal to this, which is equal to 3. Okay. 12, which is V total, equals I total. And then times R total, which is equal to 3. I total is equal to 4. Amps, right? Well, what do we know about a circuit in parallel, right? Which is what we're looking for. We're looking at the current across resistor B. Resistor B is in parallel with resistor A. We know that IT equals IA plus IB, right? The total current is equal to the current across A plus the current across B, right? No, did I make a mistake? Did I make a mistake when I was writing it? Oh, sorry about that. I believe it should be V equals IR. Sorry about that. Let me just double check, but I'm pretty confident it's V equals IR. Yeah, it's V equals IR. I'm sorry, this was a mistake, and I'll fix it right now. I'm really sorry, I made a mistake here. Yeah, it's V equals I times R, right? And I'm not sure, I think these might be also wrong as well then. But it's V equals IR, right? Sorry for the confusion. I'll fix that. Oh, sorry. I will fix that when we're going into when this is going to be sent out to you, this PowerPoint, it'll be fixed already. Okay. But just please make a note of V equals IR. Sorry about that. Yes. So where was I? Okay. So I believe I was at IT. We mentioned is equal to 4. It's also equal to I cross A plus I cross B. Okay. And again, this is Kirakas Law. So you start off, if we're looking at this node. Sorry, whoever that was. Yeah, could you please mute? All right. So if we're looking at this node, we have one line going in, which is I total, and then it gets split into this node and this node. Right. But because these are in parallel, it doesn't always have to be this way, but because these are exactly the same, same resistance, same everything, they're actually just split in half perfectly. So that means IA equals 2 and IB is also equal to 2. That would be the correct answer. B. Right. And that's because they have the same components, which is just one resistor of resistance 2 ohms. But if, for example, one had a resistance of 3 ohms, it would not be split evenly. It would be split proportionally. And yes, and the current in C, so IC is equal to I total, right? Which is also equal to IA plus IB. So in going across this one would be 4. Yes, whoever said that is correct. Right. That's because these two, this node, it splits into these two paths, but right here it then reconverges. So 2 paths go into 1 path, and 2 plus 2 equals 4. So yes, current across C would be 4. So the current I total equals 4. The way we did that is we had a V total, so we used V equals IR. We know what V total is. It's 12 because that's how much the battery was. We found the total resistance, which we calculated to be 3 ohms, right? And then from there, we just did 12 divided by 3 to separate I, and then I is 4. I total is 4. Right, because this is total, total, total. Does that make sense? Somebody who asked that in the chat. Okay. Any questions on this before I move on?
Mark, yes, I have another question. There's a little trick that I've been using instead of the flip.
Mm-hmm.
You calculated the V total for the parallel circuit. Where was that? Let's see, when we're calculating the A and B because they were in parallel. I think you did 1/2.
Right, yes, I did.
Yeah.
The way I usually do it is 1/2. Yeah, go ahead with your explanations. I read it out. Go ahead.
Is that how you got the V total?
Well, that's how I got the resistance across. No, this is for resistance. This is not for voltage. It's for resistance.
Yes, for the resistance of parallel. So there's a trick that I use where I just product over sum. So if we did 2 times 2, because it's, instead of 1, to avoid the flip, if I did product over sum, it works. Like our total is 2 times 2 over 2 plus 2, which will still give me the same answer. It's just a trick I learned somewhere for calculating the R equivalent for parallel. Product over sum, and it avoids you flipping.
Maybe, I'm not sure, but this is just the way I do it. If you find another way, that works too as well. Yeah, but yeah. Somebody asked if the resistance were different. So I said, for example, if the resistance of A was now 3 ohms and the resistance of B was still 2 ohms, you would do it this way: 1/3
Okay.
plus 1/2
2.
Mhm.
is equal to, so you have to find the least common factor. So you would do 2/6 is equal to 3/6. Right, and then you just add that up and you get 5/6. Then you just flip it to the total would be 6/5. That would be the total resistance.
Sure. And if I did the same thing with R times, you say R, if I did product over sum, I'll get the same thing. Product
Okay.
of 3 over 2 is 6. Sum of 3 plus 2 is 5. So like again, we'll still get the answer. It's just a quicker way, especially when
okay,
you tested exam. You'll always
right.
get
I
the
see.
same answer. You did it the long way and you flip, but if you do the product, 3 times 2 is 6 over the sum 3 plus 2, you'll still get the same. Just something somebody if
Okay.
you want.
Yeah, if
Avoid
anybody
all
wants
that.
that, yeah, if that
Okay.
works, then that's fine. Yeah. Somebody asked how we got 3 ohms for resistance. I just made that up right now because somebody asked, because right now they all, like the question says they all have the resistance of 2 ohms. So A, B, and C are all 2 ohms. Somebody asked if they had different resistances, how would you solve that? So I just like pretended that A was 3 ohms and B was 2 ohms just to give like a different numbers, right?
I have a question. If it wasn't in series, we wouldn't have to split it. We'll just stop at the V equals IR. And then that will be the answer. If it wasn't in series, it was just in parallel. You notice how you said you divided the the current because it went from A to B. If it was just a series, it would just be one current, right?
Yeah, if it was they were all in series, yeah, the current's the same everywhere. So you would just do four. It would the answer would be 4, right?
Okay.
Yeah, if they're all in series, yeah.
Okay, thank you.
Okay, any other questions? How would you find the current for B and A? Oh, how would you find the current for B and A? Oh, you would use good old B equals IR. Right, that's how you do it, right? Because if you, for parallel, right? Because if you look actually here, the voltage for a parallel is the same everywhere. So if you look here, you can actually do 12 equals I over whatever the resistance is here, right? And then you could just find it that way, right? I believe that that's how you do it. Actually, I think that's how you do it. Not exactly. I think that would be how. I believe that would be how. But I'm not exactly sure. Yeah, I can get back to you on that. But I don't think they'll really ever ask you that. Usually it's something like this, right? Okay, anything else? Any other questions? Okay, last time I want to talk about capacitors. This is gonna be a shorter like section, right? Because capacitors are much more complicated topic. They're also not as big on the MCAT as like just circuits or electrostatics. So I'm gonna be just covering the basics. If you have any more like advanced capacitor questions, please come to office hours with like specific questions that you might have. Or like Google is also good. But most like the capacitors themselves are already low yield, but out of the like the low yield topic, I'll be telling you what the highest yield stuff is from that low yield topic. So right, anything more specific that you is be very, very rare that you'll find on the test, right? So first we want to talk about what are capacitors. Capacitors are essentially two plates a certain distance from each other. So if you actually remember on a circuit diagram, they look like this. That's because that's what they look like in real life. it's this is like these are square like plates. This, if you have like a front view, is like a square plate, right? Like this, like think of your hands, right? If you like turn it this way, it looks like this, right? This is exactly what they look like. Capacitors, and they have a certain distance between them, d, right? Their exact function in a circuit is not very high yield, and it's a little bit complicated, and it would require like a lot more explaining, a lot more going into it, into like electrical fields and stuff. But there are some important equations that you should know regarding them. Firstly, they have units of farads or F. And somebody asked, there was microfarads, right? I believe the most common one you'll see is either microfarads or millifarads. Those are the most common scales for them. You don't really, like 1 farad is like a huge capacitance, and you'll never really see that in a question, because it's just like a ridiculously big number, or it's just like a ridiculously big thing, right? Most capacitors have either milli or micro, right? The 2 important capacitor equations are these two. Q equals C over V, and C is capacitance, right? That's the measure of a capacitor, just like resistance is the measure of a resistor. Capacitance is the measure of a capacitor. Q, is charge, and V is voltage. This is how you would maybe relate capacitance back to charge and voltage, right? Then there's also this equation, right? And this is how you actually find capacitance with a certain capacitor without knowing like the charge and the voltage and stuff like that. It's equal to epsilon 0. It's like this is like a specific number to the like the material you use, right? It's the permittivity of the specific capacitor. A is the overlapping area of the plate. So like I said, this is what they look like, right? If you got like a front view, so like this is like this. If you got like a front view like this, right? The area, like this area, the surface area of the square would be A, right? And as long as they're the same size, right? That's what A is. It's the area in meters squared. And D is the distance between the plates. So it's like this area. It's like this distance between them. That's how you find a capacitance. That's how you find capacitance. Ways to increase the capacitance of a capacitor: make the plates bigger, right? More area, bigger capacitance, or decrease the distance between the plates. If you increase the distance, capacitance decreases. Decrease the distance, capacitance increases, right? Somebody asked in the chat, is our cell phone capacitors because they store charge? Like I said, going into capacitors, especially like that, that's more like something you would ask like an electrical engineer or a computer engineer. That's a little bit more difficult. Like the purpose of a capacitor is they essentially store charge, and they have they have like constant electrical field in between them. That's much I know from like the physics I took, the undergraduate physics. If you were to go more in-depth capacitors, you need to ask like an electrical engineer or a computer engineer, something like that, right? That's not really covered on the MCAT, but yeah. So these are the 2 equations that you should know regarding capacitance. And if you just know these equations, that's pretty much all you really have to know for capacitors. You don't really have to know what they are, how they function, all that. This is the main thing you have to know about capacitors, but I'll give you a couple of extra info on the next slide. The electric field, like I said, inside a capacitor is constant, right? We haven't talked about electrical field yet, but if you already know what that is, electric field is constant. The net force in the middle of a capacitor is 0 on anything like on a dipole or something that's inside, right? If you had like a positive or negative charge, the net force on it would be 0, the electrostatic force mainly. When capacitors are fully charged, no current passes through them at all, right? And I want to actually go back to this, right? We technically, like, if this was a resistor, we know how to do resistance in parallel. We could find the current running through all of these. We have V, we have what the resistance is. How would we do it if we had a capacitor in here as well, right? Well, if it said this capacitor is fully charged, what that means is no current actually passes through it, right? So what that means is all of, like, even though these are in parallel, these two are in parallel, you can think of it as only it passes through this way, right? You can think of it only pass through this way because the current here, I at say C, which is the capacitor, equals 0. If the I here is 0, that means I R plus IC equals I total, right? So I total is the total, IR is the current through the resistor, and IC is the current through the capacitor. We know that IC equals 0, so we can actually just get rid of it. And so the I total is just equal to the IR, from the current going through the resistor, just going through this portion, right? And so you can just find the total resistance this way. Like, consider this just like a box, and you can just ignore this whole area, right? Capacitor in parallel, like current in series. Capacitors in parallel, if they're fully charged, you add them together. So if you had, like, for example, I'm gonna clear this. If you had, for example, another thing here, and this had a resistor, right? You would have to add all 3 of these resistors, right? Like normally, you'd add all 3 of these lanes, right? Because it's split 3 ways. But you'd still normally do that, except you just know that through this lane, it's 0. So you're essentially only like adding these 2 lanes for current in parallel, at least, right? Does that make sense? In series, if you had a capacitor in series, you wouldn't be given one in series that's the dimension is fully charged, right? Because the current passing through it is 0, unless there's no current passing at all through the circuit, right? And you know that the current everywhere is equal. So they wouldn't give you one in. They wouldn't say it's fully charged. And if it's not fully charged, you don't know how to do it, so they wouldn't give it to you at all, right? Because doing that is like more complicated than the MCAT goes. Okay. All right. That actually is the last slide, I believe. Yeah. So that was the last slide. Reminder: office hours are every Sunday. If you have any questions about this topic or any other topics, or if you have any specific, if you find any specific electrostatic or circuits or capacitor questions, and you're practicing, please feel free to give me. I will send out the GroupMe link right now to whoever just asked. One moment, I'm going to stop the screen share. Yeah, if you guys have any questions, please feel free to stick around and I'll be answering them for maybe another 15 minutes, 10, 15 minutes. Okay. But let me post the new GroupMe link in the chat.
Mark, you know how you said Kirchhoff's law 1, where current equal to is split? What about the voltage?
Oh,
Kirchhoff's law for voltage?
there is a Kirakas Law for voltage, yeah. One second, let me just put the group. There is a Kirakas Law for voltage. Here, let me actually just get the exact wording, just because I don't want to give anything wrong. But yeah, the sum of all the voltage drops around the loop is equal to 0. What that essentially means is that all of the voltage is also kind of, I don't want to say like conserved, but it doesn't, like the voltage doesn't leave, right? So if you started off with 12 volts from the battery, if you had voltage across like everything, it would still be like 12 volts, right? You wouldn't add or get rid of voltage, if that makes sense. The sum of all the voltage drops is equal to 0, right? So if you found the voltage drop, here, I'm gonna share my screen just because I think it'd be easier, might be easier to explain with pictures. So if you had a circuit, sorry, let me annotate. So if you had a circuit like this, right, and then you had resistor here, and resistor here, and then a battery here, right? Then you had a voltmeter here, a voltmeter here, and a voltmeter here, right? And just pretend these are all voltmeters. The voltmeter here, like the volt reading from the voltmeter here, the voltmeter from the volt reading here and here, they would all add up to 0. So the voltage drop across a resistor would be 0. Like they would all sum up to 0.
And one other question, Mark, is the current going from the positive to the rest of, or the, where does the current start? Like, so we can trace it, like if it start.
Typically, I believe
Where's
it
it
goes
going?
positive. I believe it goes this way, positive to negative.
Positive, okay.
I believe so. If you did it in the other way, you would just negate it. If you did it in the other way, you just negate it. But I believe it's positive to negative.